And after today, pretty much all of this current homework, except for maybe 2 problems, which are pretty simple. It's just practicing using the formulas for electric field near weird objects like disks and rings of charge, which we haven't learned yet. Pretty much all the first homework should be doable after this, but all of it will be doable after Monday. OK, so first thing, as promised, I didn't show this last time, but here's some reference values. You can find them in your book. You can find them on Google. But I wrote some notes here on like what the standard units are, some conventions. So if you're doing your homework and you need a place where all the electron and proton stuff is popped up, here's a slide with all the relevant information. Also, 2 things I want to remark. Separate people came up to me and asked me this question, and I thought it was really good to communicate. Some people are trying to find the x component of electric force in these problems where there's diagonal pushes going on. Some people are trying to find the x component, and I'm going to write this in red because it's not correct. It's a very good guess. Some people are trying to use the x separation in the denominator for r squared to find the x component of the force, and they're trying to plug in y squared in the bottom to get the y component of the force. It's a good idea, but unfortunately it doesn't work. The only thing that you can do is you can find the total force by using the total distance, even if it's diagonal, between the charges. And then after you have the size of the diagonal force arrow from kqq over r squared, then you're going to have to use trigonometry to find the x component and the y component of that force. Okay, so again, a very good idea. You could very well conclude that it would be correct, but unfortunately it just doesn't work out. The Coulomb's law only tells us the size of the force arrow, not each individual component of it. Something else I want to remark is just be really careful with parentheses on your calculator with these problems. There's going to be a lot of nanocoulomb garbage going on and centimeters being used. So just make sure you group that stuff in parentheses before you square it or before you divide by it, because your calculator will interpret 2 centimeters. If you try and do 2 centimeters squared, your calculator only squares the last factor instead of the 2 as well. So just be mindful of that. If you choose to use the EE key, it should automatically group the whole thing in parentheses, so you shouldn't need extra parentheses. But just be careful with your parentheses. One more remark from last time. I was having a little trouble explaining when there's a negative charge why you should use k absolute value of q1 absolute value of q2 over r squared. There was some business about, do you use another negative sign when there's a negative charge? And I just wanted to sketch an analogy in case anyone didn't get this yet. When you have a frictional force on an object going backwards, let's say it's a frictional force of 10 newtons, you don't write negative 10 newtons over your left pointing arrow. You just write the size of the frictional force, 10 newtons. And the fact that it's a negative force is conveyed in the fact that it's a backwards push. So you don't write negative 10 over the arrow because it's already pointing in the right direction. It's a force of size 10 directed in the leftwards direction. So similarly, for all these problems, if you've drawn the direction of the arrow correctly, you only write the positive size of the force above the arrow because it's already pointing in the correct direction. Another thing from last time that I want to bring up is I didn't introduce you to this thing called epsilon 0, which you might see in your homework in some places. So I want to prepare you for what that is. Epsilon 0 is just another constant that people like to use. And the relationship is that our friend k, 9 times 10 to the 9th, some people, for reasons that we'll see later in the course, prefer to write it as 1 over 4 pi epsilon 0, where epsilon 0 is this random other constant called the vacuum permittivity. Some people also call it the permittivity of free space, or just epsilon 0. And this has a value of 8.85 times 10 to the negative 12. Oops. And you'll see it in different units. It is 1 over the units of K, so it's Coulomb squared per newtons times meter squared in the denominator. But I want to point out, on Google, you will see it written in this even more gross set of units, farads times meters to the negative 1, and you don't know what a farad is yet. But just be aware that this is standard units. This is the same thing as Coulomb squared per Newton meter squared. So when you Google it and you're like, I don't know what Google's telling me, just understand that these gross units, farads meters squared, they've just regrouped the charge with the newtons and some of the newtons with the meters. So this is K versus epsilon 0. And again, we'll use epsilon 0 later in the class, but for now, we're just going to be using K. One more thing I want to remark. When you're Googling the value of K, there's another thing called KB. That's the Boltzmann constant. You use that in thermodynamics, and we'll use it later. Just be careful when you're Googling what's the value of K. Specify it's the Coulomb constant, not the Boltzmann constant, because they have the same letter. OK, something I didn't get to last time that is going to be important on the homework is insulators, conductors, and the phenomenon of induced polarization. We're not going to spend too much time on this. This is a very theoretical class in that you'll only consider like isolated charges, but it's good to know a little bit about insulators and conductors. So again, just a very quick overview of what each is. An insulator is a material in which charge cannot move. So a classic example of an insulator is either plastic or rubber. If there's some free electron stuck to the surface of plastic, if it were a metal, it would be able to move. But for plastic or rubber, the electron is more or less glued in place, not able to move, so therefore it's called an insulator. Now, something that is less intuitive about insulators is you can actually charge them up. Okay? I always thought that you can only charge up metal things, but you can definitely charge these up, and it's mostly by leaving charge on the surface. The classic example is taking a plastic or rubber rod and rubbing it with a wool cloth, and that leaves excess either electrons or protons, or it either takes electrons away or leaves extra electrons on the surface. So I'll just write down that they can be charged. This is a homework question. They can be charged. And the classic example is rubbing a rod with a wool cloth. It's just that once the charge gets there, it doesn't move around. If it got deposited at one place, it can't move. Conversely, conductors, the charge can move. And an example of this would be metal or a wire. If you put charge in and you give the charge a little push, maybe by putting another charge nearby, the charge that's in the wire is going to start flying down the wire. It can actually physically move when it's pushed. And a classic conductor example is if you bring two spheres together. Let's say I have 4 positive charges on the left one and 2 negative charges on the right one. And you touch the spheres together, the charge is going to distribute itself until it's as even as possible. So if you touch these together, two of the positive charges will combine with each of the negative charges, and the two leftover positive charges will spread out evenly across the surface of the two spheres. Okay? And the third concept here is polarization, and specifically induced polarization. Who's heard of induced polarization before? Only some of you. Who's heard of the van der Waals interaction before? Probably more of you? Okay. So induced polarization is very similar to the van der Waals interaction. So a question for you is, if I bring a positively charged rod, that was a bad rod. If I bring a positively charged rod near a neutral, let's say a soda can, a hollow ring made of metal. At first glance, you'd say, if you bring it near, nothing happens because the metal can is neutral. There's no electric repulsion or attraction between the two because there's no charge on the second one. But what actually happens, and I forgot to ask for the demo, is if you bring the rod near the can starts rolling towards the rod, even though there's no net charge on the can. Does anybody have an idea of how that happens? I'll take a hand. Yes?
Neutral object is attracted and...
Right, but what happens to the charges on the neutral object to make it happen? We'll go in the back row. Yeah? Exactly, exactly. Yeah, so although there's no net charge on this metal rod, the positive charges and the negative charges that are sort of floating around in the can, the negative charges see the positive charge and they fly over towards this side of the can because they want to be attracted to it. Meanwhile, the positive charges are repelled by the positive rod. So what happens is the charge sort of separates itself onto opposite edges of the can. And now the negative charge is closer to the positive rod than the positive charge is. So the attractive strength is going to be slightly greater than the repulsive strength. And then the can rolls towards the rod. Now, this is totally unconnected with anything else we'll do in the course, but it is a discussion problem that you'll have in your first discussion, so I wanted to go over it. Any questions here before we move on to electric field? Okay, perfect. So electric field is, well, Coulomb's law was, I guess, your first introduction to electromagnetism, but electric field is where we really start to get going into a new topic, the concept of a field, a magnetic field and electric field, which we're going to see throughout the class. So I'm going to start by giving you sort of a motivating example for electric field, just like I did last time for Coulomb's law, and it's the same example. If I have two protons near each other, we know from last class that, let's say the one on the right is going to experience a force due to the one on the left. The one on the left will also experience a force, but I'm not going to draw it for now. The question is, what actually causes that push? In the same way that for gravity, you don't really know what causes the pull of gravity, and the answer is kind of watery. It's that there's a field that exists throughout space around any charge. And when you put another charge into that field to experience the field, it's going to feel a push. Now, the notation that we're going to use is that the definition of the electric field's direction is that the electric field points in the direction that a positive charge would get pushed. We're going to get to the numerics a little bit later. But for the electric field, the direction is going to be pretty tough to determine in general cases. So we're going to spend a little bit of time figuring out the direction of electric fields before we worry about the size. For Coulomb's law, it was pretty easy. There's repulsion, and you're done. Or there's attraction, and you draw the direction of the force, and you're done. Electric field tends to be a little bit more challenging. Okay, so the electric field points in the direction that a positive charge would get pushed. So if I just erase this proton, and I ask you, what's the electric field due to this proton at this black dot, what would your answer be? Everyone think to yourselves. If I ask you, what's the direction of the electric field at that black dot, what direction is it? It should be pointing to the right, right? Because if I were to put a positive charge in here, if I were to just imagine putting a positive charge in here, it would be getting pushed to the right. So that's literally the definition of the electric field direction. If I were to put a positive charge in, what direction would it get pushed? The answer is to the right, so the electric field arrow points to the right. Now, I want you to notice something about the electric field. Beforehand, when I had the two protons here, I would always use the phrase, what is the force experienced by this proton due to this proton? When I'm talking about the electric field, I would ask you, what is the electric field at this point due to the proton? I don't mention a second object at all, because there is no second object. You just imagine what would happen if there were a second object, a second positive charge, that you were to put into the situation. Okay, so another question is, what if I replace the proton with an electron? What direction does the electric field point now? Over to the left, right? Because if I were to put a positive charge at the black dot, it would get pulled over to the left towards the electron. Okay, and again, I don't mention what's the electric field at the proton of the electron. No, I just say what's the electric field at that point due to the electron creating the field. And the answer would be over towards the left. Okay, now here's another question. And we're going to have to go in circles a bit before you see that it all works consistently with each other. In another example I did in last class, I had a positive charge and a negative charge here. And the negative charge experienced a pull to the right, or sorry, to the left. But I just told you that the electric field points to the right. So the force on the electron was not in the direction of the electric field. It was in the opposite direction of the electric field. And that is okay. That's going to be the way it works. Since the electric field points in the direction that positive charges would get pushed, and negative charges always behave oppositely to the positive charges. If the positive charge wants to get away from something, the negative charge is going to want to go towards it because the thing creating the push is positive. So the electron, or any negatively charged object, it's going to experience a push in the opposite direction of the electric field. Okay? All right, now at this point, we're going to work on sort of a big example that is tried and true. I gave this to my labs last semester. So there's 5 quick questions here that I want everyone to work on. Again, for some of you, it might be very straightforward. You might finish this in 10, 15 seconds. For others of you, it'll take a little bit of thought on this. But so there's 5 questions. Work with your neighbors, and we're going to sort of go back and forth every maybe 30 seconds as we go through each part, okay? All right, so part A, probably pretty simple. All right, let's do A through C right now. All right, A, a positive charge. Positive charge would get pushed to the right. Just by looking at the charges, I see a lot of positive charges on the left, a lot of negative charges on the right. So a positive charge put at the black dot would get repelled by these guys and attracted by these guys. So it wants to go to the right. A negative charge experiences a repulsion from the right and an attraction to the left. So conversely, it would want to go towards the left on both counts. Part C, what direction does the electric field point at the black dot? Okay, to answer that question, you just ask, what direction would a positive charge get launched? And from part A, we determined that a positive charge would get launched to the right. So answer for C would be the electric field points to the right. Okay, part D. So we found the electric field points to the right. Does that agree with this general pattern of electric field points away from positive charges and towards negative charges, like we saw on the last slide? And the answer is yes, it points away from the positive charge and towards the negative charge. Okay, now here's the real thing I want you to take away. If I were to hide the charges and just tell you, at the black dot, there's an electric field pointing to the right, could you still answer A and B? Talk amongst yourselves for about 30, 40 seconds. Especially the negative charge. Okay. So you should determine that, yes, you could still determine the direction or the answers to A and B. Right. So if the electric field points to the right, question A would ask, if I put a positive charge in that electric field, what happens to it? Well, the answer is the electric field always points in the direction that positive charges get pushed. So if the electric field points to the right, the positive charge would also get pushed to the right. Conversely, we know that negative charges and electrons get pushed backwards by the electric field. And again, that's totally okay. It's just the way life works. So the electric field points to the right, so a negative charge would get pushed back towards the left. Okay? All right, next thing I want to bring up is that the electric fields will add like arrows, just like forces do. The electric fields created by different objects. So for instance, here's an observation point, here's a positive charge, and here's a positive charge. What's the direction of the electric field at the dot due to this charge up top in red? It's going to be downwards because it's pointing away from the positive charge, which would repel it. So that's the electric field due to one of the objects. All right? And then due to this positive charge on the left here, the push would be over towards the right. Again, it's being repelled by the positive charge. Or sorry, a positive charge that you were to put at the black dot would experience a repulsion. So the electric field from the blue charge points off to the right. And if you were asked, what's the net electric field? It's the sum of those two arrows. So they add up as arrows do. So the net electric field would be pointing, fat arrow, downwards and to the right, assuming they're of roughly equal size. Okay? So here's another in-class that I want you to be able to address. This is going to be on the homework, and you'll also see this in lab. All right, so talk amongst yourselves and ABCD card at the end of like 30 seconds or so, maybe a minute. And assume they're all the same size. Anyone need more time? All right, show me the money. I see 100% C's. That's right. Excellent work. Just for the benefit of people on the recording, I'm going to quickly go over it. So this positive charge right here creates a field to the left, which is canceled by this positive charge's field to the right, right? You add them up as arrows, and they cancel out to nothing, which leaves you with this negative charge creates an upwards electric field because it would attract a positive charge placed at this point, leaving us with an overall net up. Excellent work. Okay, so believe it or not, that's the more hard part of electric field, determining the direction, or at least that's the harder part to learn. Now we're just going to figure out exactly how big the electric field arrows are. Okay, so electric field, it has something to do with the force experienced by objects because it's sort of related to the force experienced by positive charges. So the equation relating force and electric field is pretty simple. It's that all you do to get the force is you take the electric field and you multiply it by the charge of the object experiencing the electric field. And again, this answers the question of a proton's creating an electric field of strength 10 newtons per coulomb, and I put some charge in here of charge 5 coulombs. It's going to tell you how big of a force that 5 coulomb charge would feel if you popped it in there. So I'm going to put some subscript on this. The force on the experiencing charge, sorry if you can't read these because they're subscripts. That says experiencer, and you get it by taking the electric field that is already existing, and you multiply that electric field by the charge of the experiencer. So again, in this case, let's pretend I'm so far away from the proton that the electric field is 10 newtons per coulomb. That's the units on electric field, by the way. And I put a charge of size 5 coulombs into the electric field. That's the experiencer. And I wonder how big of a push does he feel? The answer would be you take the 10 newtons per coulomb, 10 newtons of force per each coulomb of charge that you put in, and you multiply it by the size of the experiencing charge, which is 5 coulombs. The coulombs cancel, and you get an answer that the force is 50 newtons. And since it's a positive charge, you know the direction of that force is just in the same direction as the electric field. Now, some people write this as a vector equation, and that's totally okay. All it communicates is that as long as Q is positive, the F arrow and the E arrow point in the same direction, which is what we already learned. For positive charges, the electric field points in the direction that the force would be. For Q greater than 0, force arrow is in the same direction as the E arrow. Okay, now let's change it up. We're always going to have to look at positive charges and negative charges so we never get faked out when we encounter a problem. What if I put a -5 Coulomb charge in instead? Again, the electric field being created by the source charge, we're still going to take it to be 10 newtons per coulomb to the right. But this time, instead of putting a positive charge in, I throw a negative charge in. Okay, well, the size of the force is still the electric field times the size of the charge. So it's still 50 newtons, but in a different direction now. You can view this either as you computed the size of the force, and then you just know that negative charges get pushed in the opposite direction of the force from the earlier slides. So you could just look at the problem and say the electric field's to the right, therefore any negative charge gets pushed to the left, and then you just use the magnitude of this equation to figure out the size of the push, which would be 50. You could also view the fact that the push is to the left as coming from the fact that if Q is negative in this equation, it says that the force arrow is in the negative E arrow direction. Actually, I'm just going to erase this so no one erroneously writes it down, but I'll put another arrow here. For Q of the experiencer less than 0, force points in opposite direction to E. And again, this is just if you take a vector and you multiply it by -1 in each component, or any negative number, the vector flips around in the opposite direction. So this is all consistent with itself. Anytime you have a negative charge, yes, there is some weirdness that the push is not in the direction of the electric field, but the equations sort of build that in to remind you if you use the vector equations. So there's a lot of consistency checking you can do on your own work as you're going through a problem. And hopefully this will help you guys avoid getting tripped up by any minus signs, because there are a ton of minus signs that appear in electricity. Okay, so using this, we can get the formula for the electric field created by a point charge. And this is a formula you will use a lot. So here's the formula relating electric field to force. And we already know that the force due to a point charge is K times the two charges involved over their separation squared. Okay? And this is also equal to the charge of the experiencer times the electric field from this equation over on the left. So if we cancel Q experiencer from both of these equations, we arrive with what's left, the electric field due to a point charge is going to be K times the charge of the thing creating the field over R squared. And here R is the distance between the source charge and the observation point that you're trying to find the electric field at. I'll give you guys time to write down that long subscript. Okay, and just like last time, so this tells you the size of the electric field, and you can draw the arrow by hand. But just so you're aware, the book will list it with this additional information. Yes, the E field arrow's size is kq over r squared. But in addition, the direction of the E field arrow is in this r hat direction, which points away from the source and towards whatever point you're concerned about. Again, sorry for the small subscripts. It says R from the source to the point that you're concerned about. Yes, question?
Can you explain how you related the Coulomb's law and
Sure, yeah. So the question was, can I re-go through how I got this formula from Coulomb's law? And the answer to that, this formula tells me the force a charge will experience due to a point charge. And the way electric field and force are related is this is the force due to electric field, and we already know this is the force you experience when you're near a point charge. So I just divided both sides of this equation through by Q experiencer to get that. But you don't need to remember that derivation. You can just remember this formula for the electric field due to a point charge. Okay, again, this is just a notation you'll see in a book. All it communicates is the size of the electric field is kq over r squared, and it points away from positive charges when q is positive. Okay, we're going to end class today with an example. Just be careful, that's nanocoulombs and centimeters. It should be doable in the 10 minutes that we have left, so give it your best shot, and I'll ask for ABCDs at the very end. I'll stop you when we have about 3 minutes left to go over it, okay? Feel free to ask me questions. By the way, over on the right, I have careful, 0.05 is not R. It's because you need to use diagonal distance. And as usual, your strategy is you draw the arrows, you find how big they are, and then you add the arrows together using trig. All right, who still needs more time on this? All right, show me the money on the count of 3. 1, 2, 3. Keep going up, keep holding them up. All right, who had a lot of trouble with this one? A couple people? All right, I'm going to give you a quick walk through it. So the answer was C, which everyone who held up their card pretty much did have. But if you answered B, I'll show you why. Okay, so I've already drawn out some of the steps here. So I computed the diagonal distance between the charge and the observation point. And this is an isosceles triangle, so 45 degrees. Okay, step 1, I drew the electric field arrows due to each charge individually. Okay, hard part's done. Step 2, figure out exactly how long each arrow is. So I used my formula K times the Q of the creator charge over the distance squared. And that comes out to give you a total length of each arrow of 5402. And I forgot to mention, the units on electric field are newtons per coulomb. There's some ways you can rearrange it, so sometimes people will write volts per meter, but we'll learn that later. So the length of each diagonal arrow is 5402. And all we have to do is add this arrow and this arrow together to get our answer. So using trig, this horizontal side right here is 5402 cosine 45. And if you compute that, it comes out to 3820 to the left. But remember, there are 2 arrows being added together. Coincidentally, the up part of this arrow cancels the down part of this arrow because they're the same size but opposite direction. And then you have to add together the 2 leftwards arrows to get a total of 7640 to the left, which is C. And the last remark is, what direction would a negative charge placed at that dot feel a force in, and how big would it be? So the electric field points to the left, so a negative charge would feel a force to the right. Good. And lastly, to get the size, you multiply the electric field, which is 7640, times the size of the charge, which is 1, to give you 7640 newtons to the right for that follow-up question. Excellent work, guys. Have a great weekend. I'll see you Monday.